Okay, this is number 3 on the thin film, double slit, supplemental worksheet packet. So here we have monochromatic light. These would be plane waves coming in. If the rays are parallel like this, it would be plane waves like that. So they hit these 2 slits. It's a double slit question. And then we get this interference pattern. So these bumps, this shows the intensity. So this is bright right here. Then right there is dark, bright, dark. So it shows the intensity. Notice the intensity kind of tapers off a little bit as you move away from this center line right here. The intensity gets less, which makes sense because you're moving away from where the slits are. But you get this nice pattern. And you should be aware if this were a diffraction grating, if we had a lot more openings here, if there were a bunch more slits, what would happen? The screen would look like what? You'd be sharper. These sharp peaks, like, that's bad. You get these sharp peaks that are like boom, boom, like that, very pronounced with no regions where it's kind of constructive, kind of destructive. It's either fully constructive or totally destructive. Very, very pronounced with the diffraction grating. But back to the double slit question. So here's what's happening. Let's just kind of set this up. So we have rays from 2 slits. Let's just go to this maximum right there. That point's a maximum. So the equations we derived. So this bottom ray is traveling an extra distance. So we have theta in there. That angle there is theta. So this distance here, right there, that extra distance traveled is d sine theta, where theta is also, if you draw a line from the center point between the slits up to the screen, this is also theta right here. So theta appears in 2 places on the diagram. And in order to get constructive, for this to be a bright spot, as it is, what does d sine theta need to be equal to? 1 wavelength, or, well, actually in this case it's going to be, this would have been 1 wavelength right here. This would be what? 2 wavelengths. So this m could be 0. So right here, this is m equals 0 for bright. This is m equals 1 for bright. This is m equals 2 for bright. As far as the darks go, there's 2 m equals 0 for dark. There's a 0 order dark on each side of the 0 order bright. So right here, this right here would be m equals 1 for dark. This right here is m equals 2 for dark. So those are the fringe orders, right? So d sine theta is the extra distance traveled, and for bright, it's going to be m lambda. And then for dark, if you're focusing in on a dark spot, it becomes m plus 1/2 lambda. You need it to be a 0.5 multiple of the wavelength. Now, there's another equation which we're going to need for answering this problem. Oh, I didn't save this. That's awesome. I can't revert it. Darn it. I forgot to save this. So the other equation that we're going to need, you know what, I'm just going to re-add this image. Okay, now let me save this. Okay, the other equation we're going to need, so we just talked about d sine theta equals m lambda, or m plus 1/2 lambda. The other equation we need is this. So let's focus in again on the second order bright. If you want to find out, let's say where a bright spot appears, so we're looking for the distance from here to there, which we're going to refer to as y. This is theta, as we said already. Now, an approximation is to say this. This is an approximation. Sine theta, well, what's sine? Sine is opposite, which is y, over hypotenuse. Well, for very small angles, wouldn't this hypotenuse basically be this distance here if theta is very small, for a very small angle? Yeah, so we're going to say that that's L, where L is this 5 meters right there. So if you take this, plug it in up here, you can get this other equation, which is y equals lambda L over d times m times the fringe order. So those are the two equations that we're going to need to answer the questions. So now let's do it. So the two equations, we've got d sine theta equals m lambda, y equals lambda L over d, all times m. Okay, first question is, what property of light does this interference experiment demonstrate? That light is wavelength. The fact that you get this interference pattern of bright, dark, bright, dark, bright, dark shows that light is wavelength. Okay, at point P in the diagram, there's a minimum in the interference pattern, so they're talking about this point right here. Determine the path difference between the light arriving at this point from the two slits. So we're looking for d sine theta. So we got a ray that goes boom like that. Oh, we're out of time.